Hello everyone, I am Kazi Samin Mubasshir and today I'll be presenting our work Gotta Detect Them All, Fake Base Station and Multi-Step Attack Detection in Cellular Networks. This is a joint work with Imtiaz, Karim and Elisa Bertino at Purdue University. So are we connecting to a fake base station? A question we try to answer in this work. By design, cellular devices connect to the base station with strongest signal. But this is not always a safe choice. An attacker can create a fake base station with a strong signal and make the user devices interested into connecting. There's no authentication in this initial broadcast messages, so devices cannot tell real from fake during the initial setup. Fake base stations are persistent problems across generation of 3GPP protocols, affecting billions of unprotected devices worldwide. Existing detection methods are often impractical, expensive, or require protocol changes. Here are some recent news where law enforcement agencies confirmed the presence of fake base stations in strategically important locations, where attackers tried to use fake base stations for surveillance and scam. In our research, we have found that machine learning can be a good solution to protect both existing and future devices without changing protocols and without extra hardware, and with minimal overhead even when users roam. We identified 5 main challenges. First challenge is there is a lack of high quality datasets incorporating fake base station traces. Second is incorporating contextual information. Same packets can be benign and malicious based on the context they are sent. Third, capturing the characteristics of multi-step attacks. Fourth challenge is combining predictions from multiple layer 3 protocols. And lastly, meeting real-time detection constraints in real-world systems. To address these challenges, we start with building the first ever large-scale FBS and MSA dataset to prepare a dataset incorporating real-world scenario. We captured traces under mobility with both legitimate and fake base stations, different attacker capabilities, and 21 different multi-step attack scenarios. We used Powder for our dataset generation. Powder is a CT scale remotely accessible large test bed by NSF. It provides the capability to deploy FBSs with over-the-air transmission in a controlled environment. It also provides the capability to incorporate real-world scenarios like mobility and signal inference in a variety of deployment scenarios. Moving forward from dataset preparation, we now discuss our FBS detection framework. The framework has 2 layers. First, the packet level classification using a stateful LSTM with attention, learning fine-grained temporal patterns. Second, the trace level classification, which classifies the whole trace as benign or FPS, learning patterns from the packet levels. For packet level classification, we need to capture not just individual packet features, but also the context they're sent in. Our approach uses a stateful LSTM with an attention mechanism. The stateful LSTM processes packets in sequence and preserves its internal state across batches. The statefulness lets it remember long-term temporal dependencies. The attention layer highlights the most informative packets in a trace instead of treating every packet equally. Attention lets the model focus on signaling events that strongly indicate an attack. This combination allows our model to achieve high accuracy even when only a small part of a trace carries the evidence of a fake base station. After packet level classification, which labels each packet independently, we perform trace level classification to make the final decision on an entire trace. Instead of treating packets as isolated events, it looks for sequence level patterns that are characteristic of fake base station. This approach offers 2 key strengths. First, it smooths out noisy or ambiguous packet predictions by using the full trace context. Second, it captures attack behaviors that only emerges when packets are viewed in order, enabling accurate detection even for subtle, slow-acting FPS attacks. For multi-step attacks, we convert traces into packet flow graphs and use graph neural networks to detect attack patterns that unfold across message sequences. To recognize multi-step attacks, we first transform each attack trace into a packet flow graph. For example, here we show the tracking area update reject attack. We begin by listing every message exchanged during the attack sequence. Then for each distinct packet type, we create a node in the graph. We add directed edges between each pair of consecutive packets, preserving the original order of message flow. Each edge is also labeled or as benign or malicious, based on whether it represents legitimate or attacker-driven behavior. This conversion turns a raw sequence of packets into a structural graph, which lets our graph neural network model learn higher-level dependencies and patterns that can be used to identify multi-step attacks. Combining all this, we have our FPS detector framework that uses two-step packet level and trace level classification using stateful LSTM models with attention to detect FPS. For detecting multi-step attacks, we use a graph-based model capturing the underlying multi-step attack. Finally, we create an Android app to deploy our solution in the UEs. We achieve a 96% accuracy for FPS detection with a false positive rate of just 2.96% and 86% accuracy for MSA recognition with 3.28% false positives, detecting all 21 multi-step attack types in our dataset. We also evaluated the system overhead to ensure our framework is practical for end-user deployment. On average, our framework runs on just 835 kilobytes of memory and consumes only about 2 milliwatts of power, which is well within the capabilities of commodity UEs. The inference time is under 1 millisecond, ensuring it operates seamlessly in real time without disrupting ongoing connections. We analyze the overhead of both of the core detection model and the entire application. Importantly, as we increase the input load, the overhead grew linearly, showing that the framework scales efficiently even under heavy traffic. These results demonstrate that our solution is not only accurate, but also lightweight, fast, and scalable for real-world deployment on user devices. To validate our framework beyond control datasets, we built a real-world experimental setup. We used two USRP B210 software radios paired with two engineering laptops running on SRStrand's open source core network and base station implementations. Alongside this, we used a mobile phone with a programmable SIM card running our FPS detection app. In this setup, our laptop USRP pair acts as a fake base station, while the other laptop and USRP pair acts as a legitimate base station. By varying the distances and power levels between them, we created diverse real-world signal conditions. This setup allowed us to test our detection pipeline end-to-end under live network conditions and confirm that our model accurately identifies fake base stations even in realistic dynamic environments. We also evaluated the robustness of our framework by testing its ability to detect unseen and reshaped attacks. For unseen attacks, we applied a leave one out strategy. During training, we excluded one attack type entirely, then tested the model on traces of that unseen attack. The results showed that no unseen attack was missed. Instead, they were consistently classified as known attacks that are closest in behavior rather than as benign. This is critical. It shows that even if a brand new FPS attack appears, our system will flag it as malicious instead of letting it slip through as normal traffic. This experiment demonstrates that our framework can generalize beyond known attack signatures and detect novel attack variants. We also tested our framework on reshaped attacks, where we deliberately modified attack signatures by altering key packet fields and message structures and order. Even after these changes, the framework correctly classified the reshaped attacks as their original types. This shows that our model is not overfitting to fixed signatures, and can generalize to variants of known attacks, which is a crucial property for defending against evolving attack tactics. To summarize, we have created the first large-scale dataset for F-based detection. We have designed a novel ML framework combining statefulness, attention, and graph learning. And we have shown it works in real time at the end-user device without protocol changes. Thank you, and feel free to reach out for any question.